Hi everyone, welcome back to CSC 348. So today is the day where you run the risk of getting Jimmy Neutron brain blasted. Today is also the day where I hope very dearly that my child hasn't become completely irrelevant yet. Um, Given that time has felt weirder and weirder recently, it's hard to tell what references people will get and what references don't. So I'm just gonna hope that I'm not too old and just go from there. Anyway, so today we are going to talk about set cardinality and how we can use functions to basically talk about when two sets have the same cardinality. So I want you to recall the definition of cardinality. We'll let S be a set if S has specifically n distinct elements. If we can count n elements in S, then we say that S has cardinality n, and we'll also say that S is finite. And remember that when we say that S is cardinality n, we write that like this, which basically says the cardinality of S equals n. So another definition we have here is that a set that is not finite is called infinite. So basically, if you can't count the number of distinct elements in a set, then we call that an infinite set. So right away, we're going to look at our first theorem, which basically says we're going to let A and B be sets. The cardinality of A equals the cardinality of B, or A and B have the same number of distinct elements, if and only if there exists a bijection between A and B. So it's a bit of a doozy of a theorem. Basically, what I'm saying is that if we know that A and B have the same cardinality, then we are able to construct some bijection, at least one bijection from A to B or from B to A. I know that I used bijection between A and B. The reason why I talk about it like this is because if we know that there's a bijection from A to B, then we know that that bijection also has an inverse function from B to A, which also has to be a bijection. So really showing that there's a bijection from A to B also shows that there's a bijection from B to A. So sometimes I'll end up saying there's a bijection between A and B, which basically talks about how there's a unique mapping between elements in our sets A and B. So if you so hopefully that wording doesn't really trip you up too much. Hopefully, but feel free to ask any questions if it does. Okay, so I'm going to start off with a proof of the forward direction, which is where we're going to assume that A and B have the same cardinality. So what we'll do is we'll actually consider two decks of cards, D sub A and D sub B, where basically each deck has one card per element of A and B respectively, and those cards have the elements of A and B respectively on them. So I have an example right here. For A equals 1, 3, 5, 7, and 9, and B equals 1, 2, 3, 4, 5. Please ignore the mistakes that I made here. B is 1, 2, 3, 4, 5. But for these sets, we're going to define D sub A as the deck containing the cards 1, 3, 5, 7, and 9, and D sub B will be the set containing the cards 1, 2, 3, 4, and 5. Notice, by the way, that this isn't part of my actual proof. What I did here was I sectioned this off with, at least I tried to make it very clear that this is an example, but I don't consider this part of my proof. I would consider the proof by itself to be complete without this example, but this example is more of a visual aid to help understand what I'm talking about when I'm talking about these decks of cards. So basically, the way we've constructed D sub A and D sub B, we've made one card per element, exactly one card per distinct element of A, and exactly one card per distinct element of B. So the cardinality of D sub A, or the number of cards in D sub A, is equal to the number of elements in A, and the cardinality of cards in D sub B is equal to the number of elements in B. And since we assume that A and B have the same cardinality, what we're saying here is that basically D sub A and D sub B have the same number of cards. Now this is going to be really important because what we're going to do next is we're going to start creating pairs of cards through such that one card is in D sub A and one card is from D sub B through the following procedure. So what we're doing is we're shuffling each deck so that we get a random ordering of cards. Then basically we're going to draw one card, each from one from A and one from B, and sort of set those two cards together as a pair. And then we'll take another card each from each deck. So we'll take our second card from D sub A and our second card from D sub B, put them together as a pair, set them aside. Then we'll take our third card from D sub A, our third card from D sub B, put them together, set them aside, and we'll keep on doing that over and over and over again until D sub A and D sub B no longer have cards. And what we're left with is just a whole bunch of ordered pairs. Now, you might remember back from the original functions video, and if you don't remember this, I would recommend that you take a look, but you might remember that we can define functions basically as a set of matchings, or as a set of ordered pairs that describe the input and the output of a function. So we're actually going to use this idea with ordered pairs. So we're going to take the ordered pairs, one with a card from A and one with a card from B. We're going to define two functions. One where the card from A is the input and the card from B is the output, and one where the card from B is the input and the card from A is the output. So what we're actually trying to do is we're trying to construct F from A to B and G from B to A such that these pairs of cards that we'll define, or that we created from this procedure up here, those pairs actually determine the mappings in F and G. So what we have is we're going to take pairs of cards C sub A and C sub B, where C sub A has element little a in A, and C sub B has element little b in B. For all of those pairs, what we're going to do is we're going to define F sub little a as being equal to little b. F applied to little a equals little b, and G applied to little b equals little a. And basically what we've done here is we've defined F and G in such a way that they basically undo each other. So what that means is that F applied to G of B equals B, and G applied to F of A will equal A. For any, and that will hold true for any element in A and B, just because of the way that we've defined these functions. So what that means is that the composition of F and G equals the identity map over the set B, and the composition of G and F equals the identity map in A. So by the main theorem that I covered in the function compositions video, this means that F is a bijection between A and B. Or rather, I guess F is a bijection from A to B, and then we also have that G is a bijection from B to A. So really, all we needed to do for this part of the proof is assume that A and B have the same cardinality and show that we can make at least one bijection between A and B. And what we have here is basically 2 for the price of 1, is that we're actually able to make two bijections between A and B. Supposing, of course, that F and G don't happen to be the identity map or something weird like that. Like there's some edge cases where maybe F and G end up doing the exact same thing, but that's not super important. You can talk to me if you have questions about that. But basically, what that means is that we are able to create a bijection between A and B. So that's the first part of the proof. The second part of the proof is a lot easier. We're going to assume that there exists a bijection between A and B, so we're going to call one of those bijections F. Now, we're going to basically apply the definition of one-to-one and onto directly. So since F is one-to-one, that means that if you remember back to the one-to-one and onto videos, since F is one-to-one, that means that every element in our codomain is mapped to at most once from some element in from A at least. So either there is one element in A that maps to Y, or there are 0 elements in A that map to Y. That's just from the definition of one-to-one. And what that means is that in order for f to be a one-to-one function, this actually restricts the size of B to be greater than or equal to the size of A. Otherwise, if B was less than the size of A, f couldn't be one-to-one because every element in A needs to have a definition in f, but there aren't enough unique elements in B to make that definition. So basically, this means that the cardinality of B has to be greater than or equal to the cardinality of A. I'm going to run a similar argument here. Since f is on 2, every y in B has at least one mapping from A. This is from the definition of on 2. Again, if you're having a hard time with the definition, I'd recommend looking at the one-to-one on 2 video again. But what this means is that since there is at least one mapping from any element from A to every element in B, that means that the cardinality of B can be less than or equal to the cardinality of A. And again, we can check, well, if the cardinality of B was strictly greater than the cardinality of A, since f is a function, f has to assign every element of A to exactly one element of B, which means that there would necessarily be some elements of B left alone if B was greater than A. So f being on 2 restricts B's cardinality to have to be less than or equal to A's cardinality. So what this means is we know that the cardinality of B is less than or equal to the cardinality of A, and the cardinality of B is greater than or equal to the cardinality of A. For both of those to be true, the cardinality of B must equal the cardinality of A. And that's our proof. Okay, so what we have here first are a couple of corollaries to the theorem that I just proved. And this corollary here basically comes straight from the argument that I made as to why if f is one-to-one, then is a one-to-one function from A to B, then the cardinality of A must be less than or equal to the cardinality of B. So we can just take this as a fact straight from the arguments that I made in proving the previous theorem. So now, what we can have is that there's a one-to-one function from A to B if and only if A is less than or equal to B. So we have another corollary of this, which says that if we have two one-to-one functions, one from A to B and the other from B to A, then there exists a bijection between A and B. And the reason why we can say this, I'll briefly write out the justification here, is that if we know f from A to B, g from B to A are one-to-one, this is true if and only if the cardinality of A is greater than or equal to the cardinality of B, and the cardinality of B is greater than or equal to the cardinality of A. This comes from this corollary up here. And this is true if and only if A and B have the same cardinality. And then by the previous theorem, this is true if and only if there exists a bijection between A and B. So that's basically the logic as for why this corollary is true. So what this actually does is this gives us another way of saying that two sets have the same cardinality. The first way came from the theorem that I just proved, which is that if you can show there's a bijection between A and B, that A and B have the same size. The second way you can do it is you can show that there are two one-to-one functions, one from A to B and the other from B to A. If you show that both of these are one-to-one, then you have that the cardinality of A and the cardinality of B are exactly the same. So let's shelve those corollaries for a little bit. I'm going to get into a couple of definitions. So I'm going to redefine infinite right here. If we let A be a set, we say that A is infinite if and only if the cardinality of A is greater than or equal to the cardinality of the natural numbers. Yes, I do mean greater than or equal to. This lecture is going to get weird because we are talking about weird properties of infinity. But basically, you can say that there are a couple of different types, like sort of sizes of infinity. And we're really going to explore that in this video right here. So we call the absolute value of, or not the absolute value, my bad, the cardinality of the natural numbers, we say that this is equal to Aleph null, where Aleph is the first character in the Hebrew alphabet. So the cardinality of the natural numbers is known as Aleph null, and it's considered to be sort of the most fundamentally the infinite set, like the basic definition of infinity. And that actually comes from the axiom of infinity, which is that there exists an infinite set that can be interpreted as the natural numbers. So the axiom of infinity, you might remember that from the proof by induction video. Regardless, we say that the cardinality of the natural numbers is Aleph null. I'm not going to test you on this. This is just some fun facts right here. And there are some infinities large enough to actually be considered a quote-unquote larger infinity. We'll talk about that as we go along. But there are a surprising number of infinite sets that you think would be a different size than the natural numbers, but when in reality they actually happen to be the exact same size as the natural numbers. So it's going to be a fun ride. So then, we have a sort of, I guess, opposite definition of infinite, which is that if we let A be a set, actually, maybe not opposite definition, but if we let A be a set, we say that A is countable if and only if the cardinality of A is less than or equal to the cardinality of the natural numbers. So A is countable if it is a finite set or if it has the same number of elements as the natural numbers. And the way you can think about that is basically A is countable if you can look at the set, if you can start at some point in the set, and you can start counting every single element of A, and if you go forever, theoretically you would be able to hit, if you go at most forever, you'd be able to count the elements of your set A in a way such that you won't miss anything. So for example, if you look at the natural numbers being 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, what I could do is I could start at 0 and then count upwards forever. And theoretically, if I was able to do that forever without having to worry about food or sleep or the entropic end of the universe, if I was able to do that forever, I wouldn't miss anything. So I could say 0, 1, 2, 3, 4, 5, go up and go up and go up. The fact that this is a discrete set means that I won't miss any elements. However, if we look at the real numbers, if I were to try and say, okay, well, let me start counting all the real numbers, 0, 1, oh, I've already skipped an infinite number of real numbers. So the real numbers are not countable. They are strictly infinite. So that actually isn't a reason why the real numbers are considered to be an infinite set that is not countable, or in other words, that the real numbers are considered to have a strictly larger cardinality than the natural numbers. And unfortunately, due to the shortened quarter, I don't have the chance to show you the proof of why the real numbers have strictly more elements than the natural numbers. It's absolutely bonkers, and it's amazing. But you can actually prove with some crazy math that the cardinality of the real numbers is actually equal to 2 to the power of the cardinality of the natural numbers using power sets. So It's some really crazy stuff, but we're not going to worry about this. Don't worry about this. I'm never going to ask you about any of this kind of stuff. Just know what the definition of countable and the definition of infinite are in terms of this whole discussion. Anyway, so now basically what we can do is we can combine the definitions of countable and infinite to say that a set A is countably infinite if and only if A has exactly the same number elements as, the exact same number of elements as the natural numbers. All right. So with all of that under our belt, you might have been eyeing this theorem, which says that the set of odd positive integers is countably infinite. Or in other words, that there are as many odd positive integers as there are natural numbers. Now, I imagine some of you may be confused, because to go from the natural numbers to the positive integers, it really does seem like you're removing half of the elements of the natural numbers in order to get all of the positive integers, right? And to be fair, it confused me too for a very long time. But when you think about it, infinity doesn't really play by our rules. So to infinity, removing half of its elements is just peanuts. It still has an infinite number of elements. And really, what it boils down to is if I started counting from 0, started counting all of the natural numbers, and you started from 1 counting all of the odd positive integers, it would take us the same amount of time to count all of them, which is forever, because they're both countable sets. But you don't have to take my word for it, because I am about to prove it. And if you understand my reasoning behind the theorem that if you understand my reasoning behind this theorem that A and B have the same cardinality if and only if there exists a bijection between A and B, if you understand that reasoning, then I should be able to convince you that the set of odd positive integers is countably infinite by showing that there's a bijection between the two. So that's the plan for this, is I'm going to prove that there exists a bijection between the odd positive integers and the natural numbers. So how do we go about doing that? Well, my favorite way of doing this is actually the method that I showed, where you propose two functions and show that they basically are inverses of each other. So the whole identity map theorem from the function composition video. You can also use the definitions of one-to-one and onto if you so choose. That is totally fine as well. I really like this. I really like the I really like the whole proposing two functions and showing that they are inverses method, because it actually helps out a lot when you're trying to find examples of, say, patterns between the two sets. So a good way of approaching a problem like this, I would say, is writing out the elements of the two sets above each other. So something like the natural numbers, we have 0, 1, 2, 3, 4, 5, 6, and so on. Then the odd positive integers, z odd plus or z plus odd, would be 1, 3, 5, 7, 9, 11, 13, and so on. Now what's helpful is we can try to find patterns between z plus odd and between the natural numbers. So if you want, I'd highly recommend trying to pause the video and seeing if you can find a function either mapping the odd positive integers to the natural numbers or a function mapping the natural numbers to the odd positive integers. Just start with one of those functions and see what you end up getting. So I'll give you a second to pause, and then when you're done figuring out your solution, your possible solution, you can resume and see how it compares with mine. All right, so what I notice is that since all of these are odd, we can apply the definition of odd to all of these numbers. So if we're trying to say 1 equals 2 times some integer plus 1, well, we know that 1 equals 2 times 0 plus 1. So this follows the format of the definition of odd very nicely. We can do the same for 3, which is equal to 2 times 1 plus 1. 5, which is equal to 2 times 2 plus 1. 7, which equals 2 times 3 plus 1, and so on, and so on, and so on. Basically, if we apply the definition of odd to all of these values in z plus odd, it actually lines up really nicely with the values in the natural numbers. And you'll see here that the integers that you multiply by 2 and then add that product with 1 to get our odd value, these integers here are actually the natural numbers, just all the sets of natural numbers. So my proposition is that we can define a function f from the natural numbers to the odd positive integers defined by f applied to some natural number equals 2 times that natural number plus 1. And we know that this is a function because it's defined for every single natural number, and the output of this function is guaranteed to be odd by definition. So the codomain of this function is indeed the odd positive integer. So I'll include something in the proof to that effect. And now what I'm going to do is I'm going to try to propose another function, a function g from the odd positive integers to the natural numbers that I think will undo this function. And I think if we do the method that we learned in algebra or calculus or things like that, where we try to find an inverse function by swapping x and y and all that kind of stuff, what we would end up getting is that we could use defined by g of m equals m minus 1 over 2. So I think these will be my functions that I want to show are basically inverses of each other. So I'll use these in the proof. So let's take a look at what the proof looks like. So we'll say, suppose f is a function from the natural numbers to the odd positive integers defined by f of n equals 2n plus 1, and g is a function from the odd positive integers to the natural numbers defined by g of m equals m minus 1 over 2. I'm going to add in a couple notes on why we know that the codomains that the functions are good. So what I'll say is that note that by definition of odd, f of n will always be odd. So its codomain is the odd positive integers. Basically, I'm justifying why we can say that f is a function. Just briefly justifying that. You can also say that, further note, that since g takes odd positive integers as input, that odd positive integers m as input, that m minus 1 is even, thus m minus 1 over 2 is a natural number. So I just want to put justifications like that to really show that, like, yeah, these functions are actually going to work as functions between the natural numbers and the odd positive integers. So from here, what we can do is then check to make sure that f composed with g and g composed with f undo each other. So now we'll say consider I'm not going to use n. I'll use x in the natural numbers. F composed other way around. G composed with f of x is going to be equal to g of f of x by definition of function composition, which is equal to g applied to 2n plus 1, which equals 2n plus 1 minus 1 over 2. And then through algebra, this is equal to n. Sorry, I switched over from x to n. Let me replace that here. I have gone big sleepy mode, unfortunately. Now what we'll do is we'll consider y in the odd positive integers and check out f composed with g of y will equal y minus 1 over 2. F applied to y minus 1 over 2 by definition of function composition, which is then 2 times y minus 1 over 2 plus 1, which is y minus 1 plus 1, which equals y. And then what I'll do really quick is I'll actually say that this is equal to the identity map over the natural numbers of x, and that this is equal to the identity map over the odd positive integers of y, just to really hammer home that we basically have satisfied the conditions for f and g to be bijections. So thus, f is a bijection. Therefore, the odd positive integers, the cardinality of the odd positive integers is equal to the cardinality of the natural numbers. So it's really trippy stuff to say that we can remove half of the elements from the natural numbers and still end up with a set that is the same size as the natural numbers. Again, you have to remember that we're talking about infinite sets here. The rules fall apart when we talk about infinity, because infinity is beyond large or massive even. Like, it's at a scale that we can't comprehend because it is so large. Our brains are extremely finite, and we can only comprehend finite things. So the reason why all of this stuff works is literally because we're dealing with infinities here. All right, so here's the next theorem. The set of all integers is countably infinite. No, I am not pulling your leg. This is actually true, and we are going to prove that it's true. Now, you might be concerned about this, and I think you'd be valid to be concerned, because of the fact that the integers stretch in both directions. So you have, for the integers, you have all these integers going towards negative infinity. Then you have -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 5, and then going on towards infinity again. Whereas with the natural numbers, if we try to line up with infinity, we could have 0, 1, 2, 3, 4, 5, and so on, which is all well and good, except for the fact that we have missed all of these integers right here. So if we're trying to count all the integers, if we're trying to line up the natural numbers to show that we can count the integers in the same way that we can count the natural numbers, this method isn't going to work, because clearly we have the integers stretching out this way and stretching out this way forever, whereas the natural numbers only stretches out this way forever. So does that mean we give up? No, we don't give up. Because I don't give up because I'm a very stubborn person, but hopefully you don't give up because you are interested in seeing this through. Because I don't know, it's cool math stuff. Um, Maybe I am a little bit of a masochist here as well. I don't know. Anyway, we're gonna continue. Um, so what I'm going to show is that we can actually find a way to rewrite the integers such that we can line them up with the natural numbers and then find a pattern. So let's consider, what if we I'm going to write down the natural numbers again. So we'll have 0, 1, 2, 3, 4, 5, 6, 7, 8. I think that should be enough. And so on. But we can look at writing the integers like this, where I'm going to alternate between positive and negative integers. So the integers starting with 0, -1, 1, -2, 2, -3, 3, -4, 4, and so on. And the reason why I'm writing out the integers like this is because we now have an ordering for the integers that only branches off towards infinity in one direction. So technically, what we can do is we can start counting the integers at 0, and they go -1, 1, -2, 2, -3, 3, -4, 4, and so on. And we'll just be able to count all of the integers that way forever. Whereas if we wrote the integers like what I had up here, we could start at some number. We could say start at 0 and go up, or start at 0 and go down. Maybe we choose to start at -5 and go up, or -5 and go down. And we'll still be missing out on a huge portion of the integers. In fact, we'll be missing out on an infinite number of integers if we do that. But writing the integers like this allows us to start at a specific focal point and then keep on counting all of the integers without missing anything. The reason why this is so important is this is what's actually going to let us define a bijection between the natural numbers and the integers. So the reason why I lined these up is not a coincidence. What I'm going to do is I'm going to circle every other natural number like this in red. So I'm circling all the odd natural numbers and also, all the even natural numbers and also all of the positive integers in one red circle like this. And I'm going to circle all of the blue natural numbers and all of the odd natural numbers and the negative integers in blue, like so. Now, what I want to propose is that we make a piecewise definition for a function that when the natural numbers are even, gives us a version of words. When the natural numbers are even, it gives us a positive integer, and when the natural numbers are odd, gives us a negative integer. So let's take a look at what that might be like. Let's define f from the natural numbers to the integers using a piecewise function. And I think I've gone over piecewise functions before, but if not, I'm totally happy to do it again. So we're going to say that f of n is equal to something given a certain condition, or something given another condition. So the conditions I want to propose are if n is even and if n is odd. I want f applied to n to do something if n is even and something else if n is odd. So you can think of it a bit like a case statement for function definition, where we say if n is even, do this, else if n is odd, do this. So when n is even, when we're looking at the red values here, I'm going to put a nice red dot here, we can see that we're matching up 0 with 0, 2 with 1, 4 with 2, 6 with 3, 8 with 4, and so on. So my proposition is that when n is even, f should divide n by 2, and that will give us a positive integer. Now, when n is odd, this is a little bit trickier because we're matching 1 to -1, 3 to -2, 5 to -3, 7 to -4, and so on. But I think the solution for this is if we notice that if we add 1 to this natural number, 1 plus 1 is 2, divided by -2, then we get -1. So let's try that out. 3 plus 1 is 4, divided by -2 is -2. 5 plus 1 is 6, divided by -2 equals -3. 7 plus 1 is 8, divided by -2 is -4. So I think that n plus 1 divided by -2 will give us what we're looking for in the case that n is odd. Now, what I want to do is I want to propose a g that I think will undo f. So, g from the integers to the natural numbers. And if I wanted to undo f, I'm going to do another case statement here, another piecewise function here, defined by g of m equals. So, since the output when n is even is a positive integer, I'm going to make the input, when m is positive, I'm going to make it output an even natural number. And when since the output here is a negative integer when n is odd, I'm going to make, when m is a negative integer, I'm going to make it output an odd natural number. So I'm going to say my cases will be if m is greater than or equal to 0, and if m is less than 0. So if m is greater than or equal to 0, this one is the easier one because we go 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and so on. So this, we can say 2m. And you can think of it as I'm also trying to undo this, and I'm trying to undo this. When m is less than 0, we can say that we would multiply m by -2 and then subtract 1. So -2m minus 1. So -2 times -1 is 2, minus 1 is 1. -2 times -2 is 4, minus 1 is 3. -2 times -3 is 6, minus 1 is 5. -2 times -4 is 8, minus 1 is 7. So this actually holds up for these examples right here. So these are my propositions for f and g. And if we show that they basically are the inverse of each other, then we will be able to see that that f is a bijection. So let's take a look at the proof. So say, suppose f from the natural numbers to the integers is defined by f of n equals the case statement n over 2 if n is even, and n plus 1 over -2 if n is odd, and that g from the integers to the natural numbers is defined by g of m equals 2m if m is greater than or equal to 0, and minus 2m minus 1 if m is less than 0. And now we need to go about showing that they invert each other. So what we'll do is we will consider n in the natural numbers, just like last time, and then show that g composed with f of n equals n. However, we have to actually take a couple cases, where the first case being if n is even, and the second case being if n is odd. So we'll say case 1, n is even, then f composed with g of n equals, other way around, g composed with f of n equals g of n over 2, and then we'll say that since n is greater than or equal to 0, n over 2 is greater than or equal to 0, which is important because then we'll know that n over 2, that will apply this case right here to n over 2. Furthermore, we'll say that since n is even, n over 2 is an integer. So we basically know that n over 2 is a positive integer, or is a non-negative integer, which means that g of n over 2 equals 2 times n over 2, which equals n, which is then the identity map over the natural numbers of n. Then we'll have a similar case for case 2 when n is odd. When n is odd, what do we do when n is odd? When n is odd, we do n plus 1 over negative 2. So g composed with f of n equals g of n plus 1 over minus 2. Now we'll note that since n is odd, n plus 1 is even, so n plus 1 over negative 2 is an integer. Also, since n is greater than or equal to 0, n plus 1 over negative 2 is strictly less than 0. Which means that we will then apply this case of g. So g of n plus 1 over negative 2 equals negative 2 times n plus 1 over negative 2 minus 1, which equals n plus 1 minus 1, which equals n, which is then the identity map over the natural numbers of n. So that's the first thing we need to show. We show that f composed with g composed with f is equal to the identity map over the natural numbers. Now we just need to show the same thing for f composed with g. So now we'll say consider m in the integers. We'll do case 3. Actually, I'll reset the count. So we'll do case 1. M is greater than or equal to 0. So then f composed with g of m, we'll take this case of g since m is greater than or equal to 0. So f composed with g of m is equal to 2m, which is clearly even by definition, which means that this is equal to 2m over 2. Since this is what f does when n is even, it will divide an even number by 2. 2m is even, so then f divides that even number by 2. So then that equals m, which is then equal to the identity map over the integers of m. In case 2, m is less than 0. So f composed with g of m is going to be negative 2m minus 1. And we can note that basically negative 2m is even. So negative 2m minus 1 must be odd. Furthermore, m is less than 0, so negative 2m minus 1 is greater than or equal to 0. What this means is that negative 2m minus 1 is guaranteed to be a natural number that is odd. So we can apply this part right here. We can apply this part of f's definition. So then, oh, sorry, I should put an f of negative 2m minus 1 here. Basically, then we get that f of negative 2m minus 1 equals negative 2m minus 1 plus 1 over negative 2, which is equal to negative 2m over negative 2, which equals m, which is the identity map over the integers of m. What we then show is that f composed with g is equal to the identity map of the integers. And we've also shown that g composed with f is the identity map over the natural numbers. So therefore, f is a bijection. So there are as many integers as there are natural numbers. All right. That was also a lot. I hope your brains are not too melted. This lecture tends to be the type of lecture that melts people's brains. So hopefully your brains aren't too unusable, but I would recommend taking a break after this. There's a lot to process in this lecture. There's 3 more theorems that I want to cover, and don't worry, it's going to be pretty easy. I'm just briefly going to give 3 theorems that are somewhat trivial to prove, and then we'll just be able to put those in your toolbox. So let me write those out, and then we'll be done for today's video. All right, so here are the last 3 theorems of this video. The first one is we're going to let A and B be sets. If A is infinite and B is infinite, then A union B is also infinite. The second is let A and B be sets. If A and B are countable, then A union B is also countable. And then finally, this theorem is basic. Actually, I should call this a corollary. I mean, it is a theorem, but we can be more specific and call it a corollary of the previous 2. If we let A and B be sets, if A and B are countably infinite or countable and infinite, then A union B is countably infinite. Now, these 3 sets are actually really useful because it can be a good way of letting us describe when a set is countably infinite by finding 2 subsets of that set and proving that they are countably infinite. So actually, what I'm going to do for your homework is I'm going to ask you to revisit the proof that the integers are countably infinite by basically taking 2 subsets of the integers and proving that those subsets are countably infinite and showing that the union of those subsets are equal to the integers. So you'll see that on the homework, and of course I'll be around to help answer any questions about that. But yeah, that is the video for cardinality and talking about stuff like infinite sets and stuff like that. There are a lot of other cool things that I would love to talk about that unfortunately I don't have the time for in this video. But if I do end up having the time and you want to see stuff like why do we say that the real numbers are infinite and not countable, or why can we say that the set of all rational numbers is countably infinite, please talk to me. I would love to talk about that kind of stuff. And some of the, I guess, quote-unquote free time that we might have in class. All right, well, yeah, thank you all so much for watching. I hope you have a wonderful rest of your day.